All right, so we come to our last talk of the day. It's a pleasure for me to introduce Brian Conrey again. He's going to continue his mini course. Brian, it's with you.
Thank you. So I wanted to talk about moments of L functions today and give you the general picture of how they behave, sort of the 2kth moment over a family of L functions. And we now have very precise conjectures for these, which include sort of all of the main terms and lower order terms down to what we think is a power savings. And these conjectures originated with the work in random matrix theory, and sort of use random matrix theory as a model to guide the way. And there are a few cases of small moments in various families where we can prove theoretically what the situation is, what the moments look like. And in other cases, we can do numerical work, and the numerical investigations completely support the conjectures that we have. Now, so this is called, we call it the recipe. The recipe is the recipe, if you have a family of L functions and you want to do some moment of that, how do you come up with the conjectural, how do you come up with the answer? Well, the way you do it is through the recipe. So I'm going to give you the recipe today. Thanks. Right, so Steve in his lectures talked about the importance of knowing about moments. They go towards the Lindelof hypothesis. If you can get subconvexity estimates, and they can tell you about equidistribution of various things. They're kind of a bread and butter for analytic number theorists. L functions or families of L functions are behind many, many arithmetic questions, and this is really sort of the kind of basic thing that we want to know. Now, normally you just want to know sort of orders of magnitude of these moments. But it's turned out, I think, after you see the answer, that the structure of the answer is nice enough that kind of makes it worthwhile sort of after the fact, in a way. When you see the answer, then you say, oh yeah, that was a good problem to investigate that. The other thing is, so moments really have to do with distribution of values of L functions, large values and things like that. John Keating talked about it as being maybe long-range correlations, not local statistics like the zeros are. And so for a long time, we thought of the zero statistics and the large value statistics as being sort of separate things, really, completely different ways of looking at things. But in the lecture tomorrow, I'll talk about something called the ratios conjecture, and there's a recipe for that, which is really pretty much the same as this recipe. And from ratios, you can actually deduce local information about local statistics, so pair correlations or neighbor spacings or whatever. And what happens is that, again, you get very precise answers, probably down to power savings. And so when John showed the pair correlation picture and said, oh, it dips down at zeros of zeta, we can sort of explain that in a way, and other phenomena. So really, all of these statistics then kind of appear as just part of the same story. Let's see. All right. So, so I just want to give mainly some examples today and try to show you how to actually do this recipe thing. And so let's start with some examples of families. so the families really kind of come in three types, unitary, orthogonal, and symplectic. So in number theory, these are the things that come up. And I don't know if it's been mentioned, but so these are not the same. So these are referring to the groups, SO, N, USPN, and U of N. And in physics terminology, these are all sort of beta equals 2 ensembles. They're not this, they're different from GOE and GSE, which don't seem to come up in number theory. Okay, so if you take any L function whatsoever and look at what happens as you go up to a large height, okay, then that by itself is going to be a unitary family. So in the Selberg class, if L of S is in the Selberg class, then so is L of S plus I alpha for every alpha in R. And so you have a whole family right there, just parameterized by alpha in R, and that's going to be unitary. Okay, so whatever you do with that, if you're looking at zeros, spacings, or if you're looking at moments or whatever, it's all going to basically have the same kind of behavior as you see for the Riemann zeta function. That was something Rudnick and Sarnak found out when they were doing N correlation, their work on N correlation of any L function, and they were completely surprised that they got the same answer in every case. The N correlation function is the same for every fixed L function. And in some ways that led to the subsequent work of, yeah. Right.
And you have a family, say, of curves, and you can, things like you got all functions off.
Right.
Then you can actually see the group.
That's what the monodromy group, you can calculate it, and then you actually know. That's right. This is all, yeah, this is all.
You just invent the group? I mean, you just, how do you know, how can you guess the group?
Well, so for me personally, I've always been like really into moments. And what happens is, if you look at the 2kth moment of the zeta function, it comes out to be something or other t times log of t to the k squared power, okay? But if you look at moments of like quadratic L functions, it comes out with a log to the k times k plus 1 over 2 power. You get a different power in the log. And if it's cusp form L functions, like the kth moment of their central values, then you get a power of k times k minus 1 over 2. So in a very simple way, from my perspective, I would say, look at the power on the log, and that actually tells you which family you're in. Now, that's not a very good answer in general, but it's practical in some sense, and it's kind of maybe possibly a quick way to see. There are very sophisticated answers that Sarnak and Templier and some people have, really gone to a lot of trouble to describe, from the perspective of automorphic representations, what the symmetry type of a family of L functions over function fields should be. But there's not that glue, we don't know what that is, that holds together the family like the monodromy group in the function field case. So it's all speculation, but it works, okay? So, so maybe we're doing mathematical physics here, I don't know. Is that a bad thing to say? Anyway, now, also if you take any fixed L function and you twist by Dirichlet characters, by all the Dirichlet characters, or all the primitive Dirichlet characters, then that also gives a unitary family. Okay, no matter what L function you start with, and that'll be a unitary family. So those are the sort of prime examples of unitary families. For orthogonal families, the second pair there, basically the simplest thing are just coming from modular forms. So if you take cusp forms, say of a fixed weight and large level, the level is your parameter going off to infinity, or a fixed level and weight going off to infinity, those give you orthogonal families. So they behave, so what does that mean? Well, what that means is let's say you take cus forms of weight 2 and level some big Q. Okay, so you take all of those, you take all the new forms that you get from there. Maybe those are all new forms. Well, at least if Q is prime, I suppose they are. And then for each one of those L functions, let's say you take the first zero, the zero closest to the, to the real line, the closest zero up the half line, right? And you just, for each one of your L functions in that family, you take that first zero. And so then you have a set of these numbers that are just those ordinates of the first zero. Okay? Well, when you do that, you're going to see statistics like the eigenvalues from orthogonal group. Okay? Or if you take quadratic, so Dirichlet L functions with a quadratic character, the Legendre symbol or Jacobi symbol, whatever. Those are degree 1 L functions, right, with the real characters. Those are part of a symplectic family in the bottom line there. And so, again, you take, let's say you take a big D and take all the little d's less than big D and take each one of the L functions for a fundamental discriminant of one of those guys and look at the first zero. Or maybe look at all the zeros up to a height of some constant over log D. So they're going to get pushed down as D gets bigger. The closest one's going to get closer to the real axis. So if you scale things in a way, if you look at a window, say, of height, 10 over log D or something, you'll have a few zeros in there for each one of those things. And if you look at the statistics of that entire set, you'll find it matches up with the eigenvalue statistics from symplectic matrices of size n, which is around the log of that D, something like that, or log of D divided by 2 pi. So, or if you looked at the moments right at 1/2, they would behave like the moments of the characteristic polynomials of USP n, where n is, again, about the size of the log of that limit that you were taking your discriminants up to. Okay? So, what? Yeah, no, that you do. Yeah, no, these are very specifically for Hecke eigenforms, new forms, primitive. That makes a huge difference. You absolutely need that. When you do the averages of moments, it's only over the primitive ones. If you throw in the rest, it messes everything up. If you throw in imprimitive ones or, whatever. No, it's everything is about the things that we're calling L functions, which are the things in, the Selbert class that all satisfy the Riemann hypothesis and have this sort of strict, analytic things that I mentioned. So it's only for the sort of good L functions in a way. You have to average over those. And it's a lot of times it's a lot of work to restrict your average, say, just to primitive Dirichlet characters instead of all characters, right? Because your orthogonality formula is much easier to sum over all the characters, primitive or not, but somehow you have to extract just what happens with the primitive ones. And so it creates extra work, but in the end, the answers agree exactly with what the predictions are. So it's quite amazing. It's amazingly successful. Okay. Or if you did, say, the symmetric square of, say, so this is a Hecke. So these are the new forms, the Hecke eigenforms for gamma naught q, let's say. Okay. All right, so let's start with a zeta function. So the classical mean value theorems, you have this result of Hardy and Littlewood that the mean square is sort of log t, and the mean fourth power, you get a log to the fourth. You can see this sort of k squared. This is a 2kth moment where k is 2. 2 squared is 4. So this 4 is a 2 times 2, and this 4 is a 2 squared. Okay, and there's an arithmetic factor there, and there's this 2 here. And those are all the moments we know, but at some point we made some conjectures based on number theory for some of the other moments. So Omet, Ghosh, and I conjectured the 6th moment, and this is our conjecture. So k is 3 here, 2k is 6, and k squared is 9. So you have the 9th power of the log on here over 9 factorial. this form of this arithmetic factor is just, this 141 is just 121, the binomial coefficients squared. Down here, 1331, just squared is what those are. Okay, so this is an absolutely convergent Euler product. You can't express it in terms of zeta functions. It's just some weird number. But down here, there's this mysterious 42. And then down here, same kind of thing, but a mysterious 24,024 that Steve Gonick and I did in 1998. And so we had this string of numbers 1, 2, 42, 24,024, and had no idea how to continue that. We had sort of a general conjecture that there's this arithmetic factor that looks like this, and there's a geometric factor that we didn't know, and the rest of it looked like that. And so in 1996, we had this conference in Seattle on the Riemann hypothesis, and sorry? Oh, yeah, sorry. P to the minus j. Thanks. Sorry. Yeah. Right. So yeah, it should be p to the minus j, 1 over p to the j here, summed there. Yeah, sorry about that. So Keating was at this conference and was desperately trying to convince the number theorists that random matrix theory was relevant to what we were doing. And Sarnak suggested to John that if he could explain the 42, because we didn't know about the 24,024 at the time, if he could explain the 42, then that would be the key to opening the door to a blissful union between number theory and random matrix theory. Is that correct? No, this is 96. It's 20 years after Montgomery's paper, yeah.
People didn't still believe that?
Well, no, but it was different because, yeah, well, so Montgomery had done his work, but then there wasn't really much that followed it. It was incredibly slow for number theorists to actually figure out what the next steps were after Montgomery's pair correlation realization. I mean, about 15 years, well, so what happened? Lisko did his work that sort of confirmed it, right, with his numerical work, where you could see the beautiful matching. And then at some point, Hedgehall did triple correlation, a super long, complicated piece of work that was almost exactly the same time as Rudnick and Sarnak did their N correlation stuff. That was in the early 90s. So already you're 20 years down the road. And that's really the first kind of thing that happened. And then that led to the Katz and Sarnak sort of theory of families, because they were trying to understand why are we getting exactly the same answers? I mean, there's got to be some differences somewhere. They thought that having sort of different Sato-Tate distributions for Fourier coefficients of L functions would lead to different correlation functions, but it didn't. But anyway, so they investigated that further, and they got their symmetry and family stuff around the same time that Keating and Snaith figured out the moments. But so the Katz and Sarnak stuff was all about local distribution, spacings of zeros and things like that, whereas the Keating and Snaith stuff is about is actually much more subtle. It's about the distribution of values. And even though it might seem obvious in hindsight, I think ahead of time, I don't think anybody believed, except maybe John and Nina, that calculating the moments of the characteristic polynomials of matrices would give insight to moments of the zeta function. Anybody disagree with that? That's right. Yeah, what are they thinking of? All right.
So come back to the story. This was 1996.
Oh yeah, so we had so this meeting in 96, and then Sarnak proposed to Keating he should do that, and he went away and gave the problem to his then student, Nina Snaith, who then they did these calculations, and as you'll see in these slides, that kind of explains these numbers and kind of really opened the door. The combination of that and the Katz and Sarnak stuff opened the door to, So, hang on, is this right? So here's some, so here's some results about moments of quadratic L functions that we knew kind of at the time. And so in particular, you can see the different powers on log. You don't see squares, you see sort of triangular numbers or something like that. And so these are 4 data points we had for moments of quadratic L functions, the last one being a conjecture. And, wait a second, did I skip a slide? What am I doing here? No. Okay, what? Right. Okay, where's my slide on moments of unitary families? Oh, well. Well, okay. Let's see. Maybe I should just write it down. I think I might have accidentally deleted a slide. So Keating and Snaith calculated the 2kth moment of let's make this a U. The 2kth moment of the characteristic polynomial of unitary matrices averaged over the unitary group with the Haar measure, and got a beautiful formula, n plus 1, n plus 2 squared, n plus 3 cubed, n plus k to the k, n plus k plus 1 to the k minus 1, and then down to n plus 2k minus 1. Okay, so your exponents go up till you get to the k, and then they go back down. And then the denominator, you have the same thing, but with n equals 0. k minus 1 to the first. And if you look at this for a fixed k, as n goes to infinity, if you add up the degree of the polynomial there, 1 plus 2 plus 3 up to k, and then back down here, you get basically n to the k squared over that same denominator. Okay, like that. And if you were to write this as gk times n to the k squared over k squared factorial, okay, so then gk is just implicitly defined as k squared factorial divided by this product here. Then you find that g1 is 1, g2 is 2, g3 is 42, g4 is 24,024. And so it exactly matches up. And they conjectured that, in fact, these are the right g's for any k. And now I've written the formula actually in a way that requires k to be an integer, but they really did it for real or even complex values of k. You can write an expression like this in terms of Barnes G functions or products of gamma functions in such a way that you can actually get gk for real part of k bigger than a half, bigger than minus a half. And yeah. So sorry, not sure what happened in my slide. And then they later did a similar calculation with, for symplectic matrices, calculated the kth moment of those, and got this formula. And that leads to a conjecture for, say, the kth moment of quadratic character L-functions in this shape with this kk plus 1 over 2 is kind of a complicated looking arithmetic factor, ak there. And that also agrees with those 4 data points. I think I just left a slide out, so I accidentally deleted it. And then a similar kind of thing for Cuss form L-functions. These are Duke, Friedlander, Iwaniec, Sarnak, and Michel, Kowalski, and Vanderkam. I guess that should be KMV. And here you see also the triangular numbers, but they're sort of shifted up by 1. So k minus 1 over 2 for these moments. And a similar calculation by Keating and Snaith for the moments of the kth powers of characteristic polynomials of orthogonal matrices leads to then a conjecture for the sort of GK that goes along with orthogonal matrices. Right. Okay, so now I want to describe the lower order terms, but maybe before I do, let's just think about the problem for a minute. So let's say you're trying to calculate this thing, the 2kth moment of zeta on the half line. And you know, well, zeta, now I know it doesn't, I know it doesn't converge, the series doesn't converge, but what do you get if you just sort of put in kind of, a sum like this? Maybe up to some range, like t to the 1 over k or something like that. Or, you like to have, if you went up to t, that really would pretty much recover zeta. If you went up to root t, then you have this approximate functional equation that Steve talked about, but you need another piece to go along with it. But let's just see what you, roughly speaking, might get. Well, if you did sort of every zeta like this, then you're going to have sort of a sum m1 up to mk and n1 up to nk of 1 over, square root of m1 up to mk, square root of n1 up to nk, and then an integral, say, from 0 to t of m1 up to nk over n1 up to nk to the it dt. Okay? Now, if the product of the m's equals the product of the n's, then you just have a 1 here, and so you get an answer of t. And if it doesn't equal 1, well, then it's spinning around, and you're going to get sort of something that might potentially be smaller. Okay? So your first thought might be that this could be somewhere around t times the sum m1 through mk equals n1 through nk. Okay? Well, if they're equal, then we can just write, say, m1 up to mk like that. And then these, maybe the mi's, they go up to something. I'm not sure what. But let's say suppose they went up to t. Who knows? Well, you've got 2 integers that are equal, and you're writing them each as a product of k things, and that's just the k divisor function, right? So you'd have some t times some m dk of m squared over m. Maybe I should make this that the product is less than t. Okay, and then you'd have something like this. Okay, so this is your first thought about how this is going to work. Now, you probably then would go to use a Peron's formula and say, well, this is just summation dk of m squared over m to the 1 plus s summed over all m times t to the s over s ds. So this would be Peron's formula. We saw this in Steve's lectures. Well, so what is this? Well, dk is a multiplicative function, and so you can write this as an Euler product. So it's product over p, 1 plus dk of p squared over p to the s plus dk of p squared over p to the 2s, and so on. Well, now what is dk of p? Well, it's a number of ways to write p as a product of k integers. Okay, well, basically, that's, p times 1 times 1 times 1, or 1 times p times 1, and so on. And so there's k ways to do it, right? So dk of p is k, so this is k squared. So this equals k squared. So it's a product over p of 1 plus k squared over p to the s plus something or other over p to the 2s, and so on. But now, what we're hoping to do is identify the polar structure of this thing, and then this integration is, let's say it's on a line from 2 minus I infinity to 2 plus I infinity, where the series, or I guess it handily converges there, but we want to move, it converges for s to the right of 0, right? We want to move the line past the singularities at 0 and hope that that gives us our asymptotics for our main term. I guess I forgot the 1 plus here, but okay. But anyway, the p to the 2s part is going to be kind of irrelevant as far as any poles go. And it's really just this k squared. And so 1 plus 1 over, so this is really like product over p, 1 plus 1 over p to the s to the k squared, and then times whatever you need to correct that. But whatever you need to correct it is just going to be a nicely sort of convergent, absolute convergent Euler product in any region that we're going to look at. And then this is like zeta of s to the k squared. So that's the upshot, is that's a zeta of s to the k squared times some ak of s, an Euler product that's nicely convergent. And so when you come back over here, you have t times 1 over 2 pi I integral zeta s plus 1 to the k squared times this ak of s plus 1 t to the s over s ds. And there's a pole at s equals 0 of order k squared, and then another pole of order 1 at s equals 0. And so you have k squared plus 1 order pole. This isn't going to matter too much, and so this is going to be asymptotic to ak of 0 log t to the k squared over k squared factorial. Okay, so this is where the log to the k squared sort of over k squared factorial kind of part of the formula comes from. And so that's how you can see quickly, maybe Felipe, to answer your question, how you could sort of you might quickly see that the power on the log is a log to the k squared. Okay, now if we were doing a similar calculation, say we were doing a similar calculation but for moments of a quadratic L-function. So what would you do then? Well, let's say you're trying to do summation d less than d, L of 1/2 chi d to the k, something like that, right? Well, so you might say we think that this is summation chi d of n over n to the 1/2 for n up to something or other, and then that to the kth power. And so we might write out summation n1 up to nk of 1 over square root of n1 up to nk, and then summation d less than d chi d of n1 up to nk, right? Bringing the sum over d inside. Okay, so now so we're thinking of this as a family, and the kind of glue that holds the family together in some ways is that there's a formula for this average. There's sort of a sensible formula for an average like this that leads to some kind of multiplicative function of n1 through nk. And that's kind of our working definition of what a family is if there's a formula, if you think you have a family of L functions, well, can you average over, the coefficients like this and get something sensible, sort of something multiplicative out of it? Now, in this case, what you might say is, well, really, if n1 up to nk, if that's a square, I mean, this detects squares, right? If this is a perfect square, then all these terms are 1, and we get d. And if it's not a square, then we get something small. So, all right, so we might think of this as being, let's say, d star, the number of fundamental discriminants, and then times the sum over n1 up to nk, 1 over root n1 up to nk. This goes up to something. We're not sure what, but with the restriction that the product is a perfect square. Okay. Now, right, and so then again, we would then go to Peron's formula and need to know the generating function of this thing. So in other words, what can you say about the generating function of that product being a square of, let's say, 1 over n1 nk to the s power? Okay, well, everything's multiplicative. This is all multiplicative, and this condition about the product being a square is a multiplicative condition, right? So this will equal an Euler product. So product over P, 1 plus now, okay, so now you have to figure out how to make this thing into a square, where the product here should be then, the simplest case is if the product there is p squared itself. So how can you make this thing equal to p squared? Well, either you have two different ends that are p's, or else you have one of them that's a p squared, right? And so how many ways can that be done? Well, if you take two of them to be equal to p, well, there's k choose 2 ways to do that, right? And then, but if you took one of them to be a p squared, then that gives you another k ways, right? So you have that over p to the 2s, and so on. Okay, and this is your k times k plus 1 over 2. And that's your power of log sort of in that family. Okay, and if you did a similar thing with Cuss forms, it's really just using sort of Pedersen formula or something like that. You just want to identify when, oh, well, you actually, yeah, that's slightly more complicated, but anyway, okay. Now, okay, so let me go on then to these lower order terms. So Ingham had actually shown that the mean square, okay, so I should say that with the Keating and Snaith thing, they had these predictions, and they found the 42, they found the 24,024, and we asked Odlyzko to do numerical calculations on this and check to see if it looked like the 42 was right. But when he did, it was nowhere near the right answer. I mean, it was off by a factor of 50 or something like that. So the 42 was not able to be confirmed numerically. We had sort of a number theoretic way to do it and a random matrix theory way to do it, but no sort of independent calculation and no hope really of doing the sixth moment anytime soon. So we started looking into the lower order terms. Now, classically, well, in the case of the mean square, there already was lower order terms, and Heath Brown in 1980 got lower order terms for the fourth moment of zeta. So there's a log to the fourth, but then there's a log cubed and a log squared and a log and a constant term. And at some point, I actually went and calculated what explicitly the polynomial from Heath Brown's fourth power moment was. And this is it, okay? And I was actually kind of interested to see if all the numbers came out to be Taylor coefficients of zeta at 1 and 2, and they actually did. The gammas are Stiltschi's coefficients at 1, and then you see derivatives of zeta at 2. At least that's how I justified spending the time to do this calculation. But that didn't bode well for trying to figure out in general, what lower order moments were. But Ingham had actually shown a little bit different thing. If you actually put little shifts in, alphas and betas, then you can write his result in kind of a nice way like this, where L is log t over 2 pi. It's a very nice symmetric thing from back in the 1920s, a pretty result. Now on the random matrix side, you can do these kinds of calculations. Let's say you have a unitary matrix and its characteristic polynomial, well, is a version of the characteristic polynomial is written like this, okay, where the thetas are, e to the I thetas are the eigenvalues. Then if you integrate over un, lambda x e to the minus alpha, lambda x star e to the minus beta, you get an exact formula, which looks a lot like Ingham's formula, where z of x is 1 over 1 minus e to the minus x. So the z of x here plays the role of zeta 1 plus x up there. And the capital N plays the role of log little t over 2 pi. And Motohashi actually had this beautiful paper with an exact formula for the fourth moment of zeta. And in there, his work really proceeds with beginning with having little shifts in the zetas. So you have two s's and two 1 minus s's. S is half plus it. So if all the shifts are 0, then this is just the fourth moment of zeta. And so he proceeded from this and then went on to develop this exact formula. But along the way, he let all the shifts go to 0. So we went back and looked at it and undid that part and massaged the main term into something that looked really symmetric. And this is exactly what it is. You have this function z of alpha, beta, gamma, delta. It's a product of, okay, so you have the alpha and beta are shifts with s, and the gamma and delta are shifts with 1 minus s. So you take alpha with gamma, alpha with delta, beta with gamma, and beta with delta. And then you have a factor in the denominator. This actually turns out to be the arithmetic factor. But you have that. And then the formula for this shifted fourth moment has 6 terms. You start with z, alpha, beta, gamma, delta. And then you swap sort of alpha and gamma. Or you replace alpha by minus gamma and gamma by minus alpha. And you put an e to the minus L alpha plus gamma out here. And then do the same thing with alpha and delta, beta and gamma, beta and delta. And then alpha and beta with gamma and delta. And so you get 6 terms like that. And once we realized that this is the form for this fourth moment, and there's a random matrix analog for a fourth moment that looks identical, then we made sort of a general conjecture about moments for the zeta function. This is joint work with Farmer, Keating, Rubinstein, and Snaith. We have a theorem in the random matrix case. This is a shorthand way to describe sort of what happens on the right side. It's kind of amazing you can fit it into one line, but using a set notation, we're able to do that. If you do a product of, so you're doing a moment with sort of A thing, alphas in A shifts by A on one thing, and then with the conjugate transpose, there's a product beta and B here for that. And the answer is you do this swappings. So your swapping sets are S and T. They have to be equal size. You take all the possible subsets and do all the swaps. And your z, you replace sort of the, if you're swapping the things from S, you take the complement of S and throw in the negatives of all the things in the swapping set T. And there's an analogous conjecture for the zeta function, except for now it's complicated by the fact that you have arithmetic factors from primes here. And so that's this A is this arithmetic factor. And so that adds a bit of complication to it. But the structure looks much the same. You just now have an A times Z zeta. Z zeta is this product of zeta 1 plus alpha plus beta, just like the Z in the random matrix case. And now we've conjectured that this is true with some sort of power savings. We think maybe a square root, although maybe that's not right. We have a very limited amount of evidence for this, but we do have a lot of numerical evidence that suggests it is some kind of a power savings at any rate. So here's an example for the sixth moment. Here's what the polynomial looks like. The 42 is this first coefficient, and you see how small it is, okay, which is why it didn't show up in the Blisko's data. For example, if you integrate up to 2 million zeta to the sixth, you get that, and our conjecture is this, which seems pretty accurate, maybe to the square root of t times some logs. Whereas if you just did the 42 and the A3, then you're way off, by a factor of like 45. Okay, so now I want to describe this recipe. And we sort of started on it over here a little bit. This gives you a little bit of an idea, but it's important to put the shifts in order to reveal the symmetric structure of the answer. We saw what a mess it was if there's no shifts and you're trying to get lower order terms in that horrible slide. But and we're going to use this approximate functional equation, at least symbolic. We're going to use it symbolically. So we have the approximate functional equation zeta like this, a sum over n up to square root of t, 1 over n to the s plus chi of s times that. And chi is a quotient of gamma factors that basically behaves like this. And now, okay, so here's what we're going to do. So we're trying to do, this is the 2kth moment of zeta if all of these shifts are 0. S is half plus it. If all the shifts are 0, it's a 2kth moment of zeta. So we put this approximate functional equation in for every single one of these terms. Forget the error term. But put that in for every term, the approximate functional equation. And multiply it out. And now the first term that you would have is much like what we did before. Well, okay, so it's this. That'll be the first term with some bounds on these things. And we only keep the diagonal terms where m is equal to n. And so the diagonal is going to be integral from 0 to t. This product of the m's equals the product of the n's. That's exactly what we did before, but now we've got shifts in here. Okay. Now think about the real part of all the shifts being positive and extend the sum off to infinity. When you do, just like down here, what we did over here, you get a product of, so now the k squared zetas now appear sort of appear like this. So let's see. Okay, so we have summation m1 up to mk equals n1 up to nk, 1 over m1 to the half plus alpha 1, and so on up to nk to the half plus alpha plus beta k. Okay? So how can we make sense of this? Well, we're just going to go straight to Euler product. Everything is multiplicative, so it's an Euler product now. And now I want to economize on variables. So in place of m1, I'm going to just write p to the m1. Okay, so I'm going to sort of reuse the variables here. And so each one of these is a power of the same prime. And so the exponents have to add up to the same thing. So this condition now becomes m1 plus mk equals n1 plus nk of 1 over p to the 1 half plus alpha 1 m1 plus 1 half plus alpha 2 m2 and so on, all the way up to a half plus beta k times nk. Okay, now it might take you a little while to convince yourself that this is actually how you do it, and that this multiplicativity in this sort of k, with a product of k things actually works. But it does. And now, okay, now we want to know the poles of this. And the poles, we're really going to be operating near the 1 line. And so we want to know what happens when we've got p to the 1 plus something or other. Well, so how can that happen? Well, okay, we have m1 times a half, m2 times a half. So whatever these are equal to, the sum of the m's times a half equaling the sum of the n's times a half, the only time we're going to get poles out of this is sort of the 1 equals 1 situation. So in other words, you can take one of these things over here to be a p and one of these things over here to be a p, and that's really the only thing of interest. Okay? And so, so if that happens, so for example, if m1 is 1 and n1 is 1, we'll have 1 over p to the 1 plus alpha 1 plus beta 1. So that's m1 equals n1 equals 1. Or if m1 is 1 and n2 is 1, we'll have 1 over p to the 1 plus alpha 1 plus beta 2. Okay, and so on. And then if you're not in the 1 equals 1 situation, like 2 equals 2, then you're going to have, you'll just have stuff that goes into the arithmetic factor. Okay, now this is really going to be product now of sort of alpha product over I and j, 1 plus 1 over p to the 1 plus alpha I plus beta j, and then times some stuff that, again, is going to go into the arithmetic factor. And then that's just like the product over I and j of zeta, 1 plus alpha I plus beta j, and then times the thing that we actually do call the a, or the script a, zeta. Okay, so this gives you your poles. There's sort of k squared things there. Okay, so now, getting a little short of time here. Okay, so, right, so that was just the first term. Now you're putting in, you have to multiply out, you have 2 terms for each of these 2k things, so you have 2 to the 2k terms altogether. But the chi factors from the approximate functional equation are spinning around super fast. But if you have chi of s and chi of 1 minus s, that's 1. Or if you have chi of s plus alpha and chi of 1 minus s plus beta, well, that's basically t over 2 pi to the minus alpha minus beta. So what we do is we just keep the terms where you have the same number of chi of s's and the same number of chi of 1 minus s's. Okay? And so, yeah, so that's this. And that gives you these sort of e to the minus L times the sum of the swapped variables. And so you wind up basically with, there's going to be 2k choose k terms altogether. So for the 6th moment, it'll be 6 choose 3 is 20. For the 4th moment, there was 6. For the 2nd moment, there was 2. For the 6th moment, you're going to have a total of 20 terms here. Each of the 20 terms has a 9th order pole But when you let all the shifts go to 0 and combine all the things, all the poles cancel, and you actually get, instead, a 9th degree polynomial. Okay, here I'm going to skip this. There's a way to write the answer using contour integrals. But yeah, basically. Okay, well, so then, okay, so I'm going to put these slides. I put them there already. Maybe I should make some corrections in them first. But I put the slides on that same website from earlier. So the slides are all there, and there's a description of how you can do, this is the, sorry, the quadratic L-function case with all the shifts that we started over here. Let's skip that. And what else do I have? Oh, right, so here's some numerical evidence for, for moments of the quadratic characters. So we have a paper called Integral Moments of L-Functions. It's in the Proceedings of the London Math Society, 2007, and there's quite extensive numerical evidence. There's a lengthy description of this whole recipe, lots of examples, and numerical evidence. For the zeta function, we go all the way up to like the 28th moment or something like that and check sort of the prediction versus the actual numerical calculation. This is some results for the 8th moment of quadratic L functions for D up to about 1 million. And the actual computation and the conjectures are pretty close. And let's see, what else do I have? Okay, and then, yeah, okay, so there's information about how to average over new forms. This is a little bit trickier. And actually, the Chebyshev polynomials come up in this. But I'm not going to show you that. Let's see. So that'll be in the slides. Yeah, this is, okay, so in the case of primitive Dirichlet L functions, so this is a unitary family, the conjecture of the 5 of us for moments in this case would be, it looks almost exactly the same as for the Riemann zeta function. But there's a slightly different arithmetic factor. And it's easier to split the thing up into sort of even and odd characters. And the case of the 4th moment, Matt Young has done this, at least for prime modulus, and gets all the lower order terms exactly as predicted by our conjecture and with the savings of a power of q. And with Ivanets and sound, we did an average over the primitive characters chi mod q, but then summed over q's, and with a very sort of innocuous integration over the, there should be y's in here. And we actually can prove the conjecture in this case for the 6th moment of Dirichlet L functions, where you take all the characters. So you have sort of a lot more harmonics. And in particular, we get the 42. So if you let all the shifts go to 0, then we recover 42 times log q to the 9th times the correct arithmetic factor. Right, okay, so this slide is just sort of showing what the zeta, it's comparing random matrix theory with the moments conjectures of what your sort of singular zeta factors look like versus the exact answers from Keating and Snaith in the case where k is integer. And you see sort of nice similarities here. Like in the symplectic case, you have this n plus I plus j over 2, where I and j are allowed to run up to k, and they can be equal to each other. The same thing is up here. And in the orthogonal case, you have I less than j. And so you sort of see the similarity playing out nicely there. These are the the Keating and Snaith formulas, where now instead of having an integer k up here, you have a real number s. So written as gamma factors. I said they could also be written as Barnes G functions. But here you see that in fact you can make predictions for real moments or even complex moments. And we have experimented with that a little bit to see if, if the conjectures are correct. But we don't have a good formula. Like let's say we want to do the first moment of zeta. Then that's k equals 1/2, so it's a fractional thing. So you're going to get a t log to the 1/4 of t. And then probably the next term is going to be t log to the -3/4, then t log to the -7/4, and quite possibly an infinite series of negative exponents. Much like if you're trying to, like in the prime number theorem, if you didn't know about lie of n, you just had, n over a bunch of powers of log. So we don't know what the analog of the sort of lie of n is here. And so we don't know, we can calculate individually what the second term should be and the third term should be, but we don't have a handle on what the whole thing should look like, let's say in the case of the first moment of zeta. And so Keating and Snaith have a conjecture for the first moment of zeta. I don't think I have it written down here. Maybe I'll bring it next time. But it's impossible to check that numerically because, well, we can sort of check it, but we can't check it in the way that we've checked these other things. It's really convincing. If we have an asymptotic series, we don't actually know where to stop taking, like how many terms to take. And so it's slightly unsatisfactory. It'd be nice to be able to do that. But in the random matrix case, they have exact answers. And, but there's no arithmetic factors, no primes here. Okay, thank you.